Hello and welcome to today's webinar, Helios Project, New Technologies Leading to Safer Skies, hosted by Orolia. My name is Christian Belleux, and I am the Aviation Product Line Director at Orolia. We are also fortunate to be joined by several excellent speakers today. Mr. Alain Bouhet, Program Coordinator at Orolia, Yoan Gregoire, Radiolocation Engineer from CNES, French Space Agency, Mr. Didier Delcuvelery, Search and Rescue Expert from CNES, the French Space Agency, Mr. Alexandre Tahbaz, Aircraft Retrofit Program from Air France Industries, Mrs. Carmen Aguilera, Marketing Development Officer from European GNSS Agency, and Mrs. Anna Bodero, Head of GNSS Department from Enaire. Before we get started, we've got a few housekeeping items to cover. This webinar is being recorded for those who are unable to join us live today. We encourage you to submit questions during the meeting through the question panel you see here on the right. Our speakers will answer as many questions as possible during the Q&A towards the end of the meeting. If for some reason you lose your connection to the meeting, you can join again using the same meeting link. Our agenda for today includes presentation from each of our speakers. Alain Bouhet will kick off this session by presenting the framework and requirements that led to the creation of the Helios project at the origins of the new Ultima-DT distress tracking beacon, the ELT-DT from Orolia. Then Yoan Gregoire will introduce us to the recent flight test conducted on the full Ultima-DT system on board in real flight conditions. Alexandre Tahbaz will then tell us a bit more about the related ELT-DT system, White STC, a certification package to implement new ELT-DT beacons such as the Ultima-DT. To follow, Carmen Aguilera will discuss about data distribution and remote ELT-DT beacon activation service. Anna Bodero will then discuss the Enaire experience about using the Galileo remote activation capability during the Ultima-DT flight test. Alain Bouhet will then conclude this session by presenting the final conclusion of the Helios consortium following the test flight of the Ultima-DT system. We will finish up with a Q&A session and the next steps. Now we'd like to begin the presentation with Alain Bouhet, presenting the context around the Helios project. Alain, this is for you.
Thank you, Christian. Good day, everyone. Indeed, in this part, I will present you an overview of what is the Helios project and what was our flight test plan, built in accordance with current regulations and requirements coming from ICAO or EASA, and other specifications like Eurocator or TCA. I will also present you the description of the system under test at the date of this testing, which was end of November 2020. And at the end, I will finish with which equipment were on board the aircraft and the various flights that we defined to meet several realistic scenarios and get the maximum of results. Sorry, I'm clicking. Oops. Okay, sorry. So about the Helios project, funded by the European GNSS Agency, this is simply the largest European initiative, kicked off early 2016, while the GADSS concept of operations was published at the same time. This project, led by Orolia, includes major well-known partners in which you can find for aviation deliveries, the French National Space Agency, aiming to provide expertise on the system level, but also standardizations, Cobham as aircraft fuselage antenna manufacturer, and two major aviation players such as Airbus for the line fit supply to airlines, and Air France Industries as retrofit solution provider, and Orolia for the coordination of this consortium and as distress beacon manufacturer for the delivery of ELT-DT. All along this project, all people involved in this process usually contributed to all the plan actions, including one of the last major action, a flight test end-to-end validation that we will present in details today. And who were involved in this process and for what? So first, this was to verify all existing key requirements and standards available today from ICAO, Annex 6, EASA, CAD-GEN MPA 210, ARANC, Eurocae, and several operational entities and technical entities have been involved to ensure an accurate verification of the full system in multiple conditions and multiple regions. It involves operational units like airline operations, here from Air France, Iberia, and from French and Spanish institutions for air traffic controls, rescue coordination centers, but also technical units from the International Search and Rescue System named COSPAS-SARSAT, involving several units based in Europe. And this is with this operational chain that the airborne system was connected to address the location of an aeroplane in distress, either in flight or on ground. So to understand the challenges and the changes happening to the commercial aviation, let's go backward a little bit in terms of regulations and finally the environment. This picture shows you the principle of ICAO GADSS approach, a performance-based recommendation to the member states, aiming at determining the location of an aircraft in distress situation till its point of end of flight. Actually, EU and EASA are applying this principle by also adding the need to be able to continue to locate the crash site after the accident if the environment is survivable. So as soon as a distress event is detected in flight and or ground, the principle is based on the alerts broadcasting in an autonomous manner to avoid any potential transmission disruption due to loss of power, fire on board, or whatever issues the aircraft may face during this type of situation. Note that installations of such equipment should happen in 2022 to be ready to deliver new build aircraft from January 2023 as required by ICAO or the EU mandate. And this concept induces the known requirements from EASA or specifications developed by COSPAS-SARSAT for its system to meet the expected results, meaning that the aircraft should have to be located even with extreme conditions of flight, for instance, with high speed, high back angle, or with a high repetition rate, which is actually exceeded by COSPAS-SARSAT specifications today. In addition, you can also see requirements and specifications in terms of accuracy and timing at system level, like the 200 meters or 99% of detection probability, which have been verified during this flight test. And this is exactly what the Helios flight test end-to-end validation wanted to verify within a system, as much as possible meeting the final system design, as shown here in the picture on the left-hand side. Except for the latter, which is coming centralized database developed by ICAO for ADT, the COSPAS-SARSAT space segment and ground network in EU have been involved in multiple mission control centers, able to process the alerts from the aircraft and to notify these alerts and the location of the aircraft to the search and rescue units. And you can note that in this system architecture, the SAR units are also connected to the air traffic service units and the airline operators. And to illustrate what we did in terms of flights to activate all these entities, procedures, and what we install on board, the next slides will show you how we proceeded. So first, for the flight test plan, it has been built in three major parts to verify all ICAO GADSS and EASA aspects. The first one was a flight determine the system performances in distress and in severe conditions as required by EASA. So we tested the evolution of the detection and localization during key 3 sequences. First, a climbing phase, simulating a change of altitude and loss of aircraft power, triggering the distress tracking as required by the European ED237 called by IK1Xs. Secondly, with 4 severe turns in each cardinal direction, we have tested the change in attitude and the aircraft position versus the SAR GNSS satellite positions in the sky. And at the end, during the descent and landing phase, simulating a change in altitude till the point of end of flight. The second testing were more focused on data distribution for both distress tracking, but also testing the operational procedures described in the new European ED277 document about emergency locator transmitter remote command capable. We will also come back later on this specific point. The flight plan you can see on the left-hand side and applied during this sequence was planned to be able to transfer the flight responsibilities from France to Spain and to test several scenarios with several airlines, Air France and Iberia. So very complex data distribution, which is the most best case. The last one was the post-crash situation and the continuous location of the point of end of flight, even after a crash, thanks to the offered crash survivability capability of the ELT-DT system on board. And to transmit alerts and the information inside the distress messages, like the positions, altitude variations, mean of activation, Orolia and Cobham supplied equipment qualified at what we call permit to fly level, meaning that key requirements from COSPA-SARSAT or EASA were already met and allowed to fly safely, including for new lithium battery regulations. So you can see here that the Cobham ELT-DT antenna was installed on the top of the fuselage of this Falcon 20, as expected by the standards. And the Orolia emergency locator transmitter, the Ultima-DT, was installed in the cabin connected with a trigger in-flight simulator based on a RM bus and to the aircraft 28 volt for the aircraft power. The permit to fly level was also ensuring that the alerts could be processed in accordance to the technical and operational standards as expected, in particular the processing, the decoding of the messages, but also the distribution of information to the relevant SAR units in alert. So now I give you back the floor, Christian, to let Yoan explaining us the results in terms of performances of the system today.
Thank you very much, Alain, for this very good introduction and presentation of what we've done. So next we have Yoan Gregoire from CNES, the French Space Agency. Yoan, it's your turn.
Thank you, Christian. So good day, everyone. My name is Yoan Gregoire, and I work as a radiolocation engineer in CNES, the French Space Agency. I have been involved in the Helios project as a coordinator of technical activities related with COSPA-SARSAT, and in particular, I worked on the MEOSAR performance analysis of the Helios in-flight test that I am just about to present. So first of all, let me recall briefly the basic principle of MEOSAR for people which may not be familiar with this system. So when a distress beacon is activated, it transmits a signal in a 4.6 MHz frequency band. This signal is relayed to the ground by MEOSAR satellites. Today, these satellites are mainly Galileo and GPS satellites equipped with a SAR repeater. But there are also satellites from the GLONASS and BDS constellations that are equipped with such repeaters, but not yet fully qualified. After being relayed by satellites, the signal is received by ground station named MEOLUT. The MEOLUT can receive the signals through several satellites at the same time. MIOLETs are in charge of detecting the signals, demodulating its content, and computing an independent location thanks to the difference of time of arrival and frequency of arrival measured over the different satellites. Then the location produced by the MIOLET is sent to its associated MCC, which will be in charge to distribute it over the COSPAS-ARSAT network. In case of an ELT-DT, the distribution will also include the MCC associated with the aircraft operator. So for example, the distress information is relayed to the French MCC if it concerns an Air France flight. So I won't go into additional details regarding the distribution of the distress information. Some of this information has already been introduced by Alain in its presentation. So I will just finish this introduction by recalling that the MIOSAR system is in its early operational capability phase, and that various MIOLETs are being deployed worldwide, most of them being already commissioned. And today's presentation is focused on the new ELT-DT standard that has been developed through the past years and for which the Helios project has been a significant contributor. So as already introduced by Alain in its presentation, different tests in flight have been performed, and one of them, which was called the test number 1, aimed at evaluating the detection and location performance of the MIOSAR system for an aircraft in adverse flight conditions. We also took the opportunity of such a test to evaluate the impact of the aircraft fuselage on the detection performance of the distress signal. So you've already seen the overview of the trajectory, which is presented on the left side of the presentation. And on the right side, you can find some details about the evolution of the horizontal speed, which is represented in blue, and on the evolution of the roll angle, which is showed in orange. The numbers 1 to 4 help to make the correspondence between the trajectory and the evolution of speed and roll angle. So you can note that the average speed during this test was about 150 meters per second during the flight, so about 300 knots. And the roll angle during the turns was up to 62 degrees. So here on this slide, the image simply illustrates the successive position of the aircraft during one of these turns. And each time there is a distress signal transmission. During the turns, the distress signal was transmitted once every 5 seconds in order to collect a maximum of data during each turn. Obviously, the aircraft that is shown here is not the one that has been used during the test, but is just for representation purpose. Now, let's go with the results of the performance analysis. So the data on the ground were collected at the European MIOLET. So this MIOLET has a special architecture with 12 antennas being distributed over 3 sites in Europe, as shown on the map, which is on the right. As you can see also, the test in flight occurred in an area which is closed to the middle of the 3 sites. We will discuss this after. So during this test, a total of 343 bursts were transmitted by the beacon, and all of them were correctly received by the European MIOLET. The detection probability is then 100%, and obviously this result is compliant with the COSPAS-ARSAT requirement, which requires that 99% of the burst be detected over any 1 minute period. But we have also looked at the distribution of the number of satellites per which the signals were detected. Here, it's important to note that all the signals were received through at least 3 satellites, and that 90% of the transmitted signals were received by at least 8 satellites. So this result demonstrates the good robustness of the MIOSAR system, which allows to receive the same information, the same distress information through several channels, and then reduce the chances of receiving erroneous data. Then we have looked at the encoded location accuracy performance. So here we have compared the distance between the location computed by the internal GNSS receiver of the ELT-DT and the reference trajectory, which was provided by the aircraft avionics. So the raw results of this analysis are presented in the first column of the table. And the typical error is about 200 meter, 250 meter. But something that must be taken into account is the fact that there is some delay between the computation of the location by the beacon and the time when the signal is effectively transmitted by the beacon. And the current ELT-DT specification allows for a delay up to 2 seconds. So in our case, the aircraft was flying at a speed of 150 meters per second, meaning that in 1 second, the position of the aircraft changes by 150 meters. So this is a major contributor to the aircraft location error. The exact encoding delay for this beacon has not been measured accurately during this test, so it was chosen to make a compensation with a 1 second delay, which represents the middle value of the specification. The results obtained with this compensation are presented in the second column of the table, and we can see that the encoded location accuracy is now typically around 100 meters, which is the kind of expected result. A final comment related with this delay compensation. This is something important for the accuracy analysis. However, in practice, an MCC would correct the timing associated with a location by 1 or 2 seconds. So for example, instead of having a location associated with the timestamp, let's say 11 hours, 45 minutes, 12 seconds, the timestamp would change to 11 hours, 45 minutes, and 11 seconds, which is not very useful information for SAR operations. Then we have analyzed the accuracy of the locations computed by the MIOLET. So these locations are independent of the location transmitted by the ELT-DT and are computed thanks to the difference of time of arrival and frequency of arrival of the signals. So among the 343 transmitted bursts, the MIOLET could compute 334 single burst location, meaning that the location probability is 97.4%. The location accuracy computing among these locations is presented in the table, and you can note that 95% of the locations computed have an error of less than 5 kilometers. And the picture on the right shows the trajectory, and each color dot represents one of the computed location. The color scale gives the location error. When it's blue, it means that it's accurate, and when it's red, it means that it's not accurate. So these independent location results are very good, especially considering that locating a fast-moving beacon is a challenge for the MIOSAR systems. And we also think that these results are probably close to the theoretical limits achievable by the system with the current standard. I will now introduce the last part of our analysis. So on the image displayed, you can see the successive position and attitude of the aircraft during one of the turns. And the line with the blue colors represent the direction of one satellite in particular, which relayed the signals. The color of the line only represents the estimated signal-to-noise ratio. You can observe that during the first part of the turns, for 3 transmissions, no signal were detected through these satellites. So taking into account the direction of the satellites and the attitude of the aircraft, we can imagine that the aircraft fuselage has masked the direction of the satellite, this satellite in particular, during this part of this turn. So this is just an example to illustrate the potential effect of the fuselage on the signal detection, but then we have studied this in more detail. Yes. So in order to take benefits of all the transmissions made during the test, we have calculated the direction of each satellite in the aircraft local reference frame, obviously taking into account the evolution of the aircraft position and attitude during the complete flight. So what is currently displayed on the screen is a so-called sky plot representation. The figure on the left shows the top view of the aircraft, while the picture on the right shows the view from the bottom of the aircraft. So let's look first at the picture on the left, and we can note that the aircraft local reference frame signals are being received in all directions on the upper hemisphere. But now, if we look at the picture on the right, we can observe that signals are being received up to minus 30 degrees of elevation in the aircraft local reference frame. So this result indicates that it is possible to receive the signal that were transmitted to a satellite that was effectively below the local horizon of the aircraft, while the transmitting antenna is in top of the aircraft. So based on this first observation, we have evaluated the detection percentage as a function of the various elevation ranges. So in order to do such a computation, we had to collect the information of which satellites were tracked by the European MIOLUTs, and then it was possible to compute the ratio between the number of received signals and the total number of signals that could have been received in an ideal system with no masking effect. So we got the result that is displayed currently on the screen, and we observe that there are 2 main areas where the detection performance is altered. So the first one, which is on the left part of the figure, concerns the very low elevation angles between -10 and -40 degrees of elevation in the aircraft local reference frame. So it seems clear in this case that this degradation in detection performance is due to the aircraft fuselage, but still this is not as severe as expected because we can see that we have at least a percentage of 40% of detection probability in this case. The other effect that was noted here concerns the high elevation angles that is at the zenith of the aircraft. And this degradation is very likely due to the antenna diagram that was installed on the aircraft. So this is not displayed here, but the measure antenna diagram as a whole in the zenith direction, meaning that less power is transmitted in this direction, and so the detection performance is lower. So in conclusion, during this test, we have observed first an excellent detection performance, which is compliant with the COSPAS-ARSAT requirements. We have also observed an excellent encoded location performance, again compliant with requirements. And we have also observed very good independent location performance, which were well beyond expectations. However, all these good results have to be mitigated by the context of the test. The European MEOLUT, as I said, has a specific architecture with its 12 antennas distributed over 3 sites in Europe, and the test took place almost in the middle of the area covered by this MEOLUT. So consequently, these results were obtained in favorable conditions, and it's likely that results that would be obtained on the edge of the coverage or with a different MEOLUT system may not be as good as the one obtained during this test. Then regarding the study of the aircraft fuselage on the detection performance, the results are reassuring. As it is shown that it is possible to receive signals at negative elevation angles in the aircraft local reference frame. This means that during a distress situation where the aircraft may have an extreme attitude angle, it is very likely that distress signal could still be received through at least one MEOSAR satellite. So I have finished with my presentation. Thank you very much for your attention.
Thank you, Yoan. Thank you very much for this detailed analysis, very interesting analysis. Our next speaker is Alexandre Tahbaz from Air France Industries. Alexandre, whenever you're ready.
Thank you, Christian. Good afternoon to everybody. My name is Alexandre. I am in charge of aircraft retrofit programs within Air France organization. So Air France responsibility on this great partnership was to assess the feasibility of installing this new beacon on a retrofit basis. Okay, so on an aircraft that's already flying, and to install this new system on this old aircraft. So we have a chance to have our own design organization approval within our company, and we also have the chance to have our own aircraft. So basically, we just used our internal DOA and one of our A320 as a use case for that STC. And we said, okay, let's build a team and let's proceed just as if we were installing the system for real on our aircraft. Okay, so looking at the system architecture from the aircraft point of view, the scope of the modification is, I would say, very standard and pretty straightforward. Basically, it's about removing the old ELT beacon to install the new one. This ELT beacon is connected to its own antenna. The antenna is installed at the rear of the aircraft on the top of the fuselage. The ELT beacon is connected and controlled using a control panel that is in the cockpit for the pilot. And finally, this beacon is also controlled and in communication with the aircraft computer, okay, which in case of the A320 is called the DMU, but on other aircraft type, this has other names. So that's for the system architecture. One point I would like to highlight is that, as you know, probably you all know, when you bring a change to the aircraft configuration, you need to follow all, I would say, a set of guidelines given by the EASA, if you're European company, or by the FAA, if you're American. So in our case, that was the EASA. Normally, we have to follow the rule given by the EASA on a document that goes the CNES. The point here is that this current document today do not provide guidelines for these brand new innovative ELT-DT systems. So we based all our certification strategy on a draft proposal issued by the EASA that is called the EASA NPA 2020-03. All right, so how did we proceed and to go with the certification scheme. So the first one, of course, our people here, they issued all the installation instructions for that new system. Okay, so based on the scheme I just showed you earlier. They also designed all the rack and bracket, disconnect, etc. All the, I would say, the aircraft parts that are required to do the installation. So that's, I would say, the first big step to install the new beacon. And then we very quickly we started to look at the certification work, which is of course the core of our added value here. First, as you can see, we are installing a new antenna on the fuselage. So we had all the structural aspects to look at when it comes to removing an old antenna, preparing the fuselage for the new one, and then doing all the calculation and the analysis of the load of the new antenna on the fuselage. That's, I would say, the first point. And then the second point is all the safety analysis and the AMI analysis we have to do for this new system. Okay, so the safety analysis is one of the key documents you have to provide to the EASA when you do such big avionics change on your aircraft. The EMI, so electromagnetic interference analysis, again, is work that is absolutely required to demonstrate to the authorities that the new antenna and the new system we're bringing on the aircraft do not interfere with the already existing system on the aircraft. And I would say vice versa, that the already existing system on the aircraft do not alter the GNSS signal that is needed to operate the beacon. Okay, so all those work have been done by Air France engineer and more precisely by Wasila, one of our engineer. And it has been done on a simulation basis. Okay, so we have tools and we have knowledge to do that. And those simulations are also completed at the end by a bunch of testing that will be required to do on the first aircraft prototype. Okay, of course, since we didn't actually modify the aircraft, we didn't went into that testing process, but the first aircraft that will be modified in the future will have to go under those testing. And then, of course, one of the other topics we look at is the electrical consumption of that new system. So it's a document that we call ELA, electrical load analysis. Again, it's pretty standard and normal when we do an STC. And finally, we issued all the continued airworthiness instructions that will allow the operator to operate the aircraft for the next years. Okay, so for us it was we really managed this project just as if it was a real STC that we had to conduct. We just stopped the whole process right before submitting all the package to the EASA. Okay, but otherwise we did everything just for like normal STC, and our conclusion is that it's a very easy modification to do on an aircraft. And from an operator point of view, it's really a good system. Okay, I'm done for my part.
Thank you, Alexandre. Interesting to see all the work done on real aircraft. In fact, that's very, very good. So now we have Carmen Aguilera, head of section of safety critical application in market development from European GNSS Agency, GSA, and Carmen, who was Helios Project officer. So Carmen, stage is yours.
Thank you very much, Christian. And I have to start by saying that it has been a pleasure being the Helios project officer. I'm very happy to share the results with the rest of the participants today.
Thank you.
So today I will explain one of the areas of activities of Helios that was related to the development of a concept of operation for remote beacon activation. In fact, the concept for remote beacon activation and deactivation is a new proposed feature within the ADT concept that is designed to be complementary to automatic and manual triggers. It's not intended to replace these functionalities. The operational procedures for this concept have been explained in the new EuroCAE standard ED277, and we will go in details afterwards, but it's already available for consultation, for purchase and consultation in the EuroCAE website. It is important to say that the concept of operation were consulted with the stakeholders involved in the process, in particular airlines, airline associations, air traffic controllers, ANSPs, RCCs that are confirmed during the description process and the different flights test that we will see later on that the process fits within the existing operational procedures and there is no clash with the existing ones. Also, the work addressed the cybersecurity aspects to confirm that the scenarios have an acceptable risk. And it was successfully validated in the last flight test of Helios. And the whole concept is developed in full compliance with the related and relevant ICAO documentation. So in short, this is the content of the ED277 that is describing the maps for aircraft emergency locator transmitter remote command via return link service. It is describing the characteristics of this potential service. And the document is targeting service providers and users of the return link service, and the focus is on the high-level concepts and typical functional interface user requirements so that this concept can be implemented by any GNSS system or by any service provider that would be interested in implementing it and offering it. This slide represents the high-level concept of the remote beacon activation and deactivation. The starting point of the whole process is takes into consideration or assumes that the aircraft operator is performing normal tracking of the aircraft in their fleet on a worldwide basis according to the specifications in ICAO annexes. However, if the aircraft operator would miss 2 normal tracking position reports, then the aircraft operator may start the process with the corresponding air traffic controllers and RCCs to identify what is the potential, whether there is a potential distress situation that may require, if also the contact with the cockpit is lost, that then in this case may require or may lead to activation of the beacon. We will see later on also which additional conditions need to be put in place and which conditions need to be met in order to enable an aircraft operator to require the activation of the beacon from the ground. In case these conditions are met, the aircraft operator may require the activation of the beacon from the ground by requesting it to the service provider. That would also activate would issue the request to activate the beacon or the ELT-DT on board the aircraft. The distress message would be then transmitted by the beacon, and finally the COSPAR system of the underlying infrastructure would provide the position of the aircraft back to the service provider and also to the aircraft operator. We will go now in detail of the different functions. It is important to highlight that the remote activation shall be used only after declaration of the TRESPA by ATSU. That is, in case the aircraft operator misses the corresponding position reports, according to the ICAO Circular 347 and in accordance with the different definition of distress phases in ICAO Annex 11. Then in these cases, the aircraft operator, in dialogue with the ATSU and the RCC, may declare a situation of the TRESFA. Only in case a situation of the TRESFA is confirmed by all the entities involved in this dialogue, once the position is lost and the contact with the cockpit has been lost, only in that case, the aircraft operator may go to the next step, and that is requesting the use of the activation of the beacon. So in that case, also only authorized users can access the service. That means only users that have been concluded an user agreement with the service provider would be entitled or could request a remote activation or deactivation of the beacon. In order to get authorized as an user, the user, in this case, we are taking as the example the aircraft operator, would need to conclude a user agreement and register to the service provider database by providing a set of information that includes a point of contact, aircraft ID, beacon ID, so that when a request is received, the service provider could activate the required beacon. And the service provider, on the other hand, is responsible for managing the authorization of the users, providing authentication, hosting a database, and validating the service requests of the authorized users when this request arrives to them. Also, the concept of operation envisages the availability of a smart user interface to also limit potential human errors when a request for activation or deactivation arrives. That means when an authorized user, under the conditions that we just commented before, request activation or deactivation to the beacon, in this case, the user interface would identify what is the aircraft ID of and the beacon ID of the beacon that should be activated. The user interface also asks the authorized user to confirm that the TRESFA has been declared by the corresponding ATSU, and also performs additional validation activities in order to ensure that the user that is requesting the activation is really entitled to do so. In these cases, the user interface would launch the request for activation or deactivation to the concerned beacon. As a summary, and also to highlight other important topics, this graph is describing the whole process, and also describes the different methods put in place in the concept of operation to ensure that there are robust measures that ensure that the process is solid and is robust, so that in case of a request, the correct beacon is activated or deactivated, and only an authorized user is receiving this service. So as a summary, the user that requests activation needs to be authorized in advance and before requesting the activation. The service facility implements a user authentication functionality. There needs to be in place a smart user interface, and that again prevents from potential human errors and in updates and maintains updated the related information for beacon users and the aircraft that could be involved in the service. And finally, also the request must be validated before launching a request for beacon activation or deactivation. This is the process that we put in place during the flight test in Helios project, and that Alain will explain in more detail.
Yeah, thank you, Carmen. Okay. So as you can see here on the map, so this is a pure example of what Carmen explained just before. So we have verified with a flight controlled by Air France operations, the case of a distress tracking activation in the French airspace, going through the Spanish border and entering in the Spanish airspace. So in addition to the change of the airspaces and air traffic control accounting areas, the advantage of this route was also the opportunity to change the search and rescue region, as explained at the beginning. So because the search and rescue region is different from France and for Spain. So multiple airspaces and multiple SAR regions, meaning different air traffic service units and different rescue coordination centers, which were involved in this process. For your information, we also tested with Iberia operations, other scenario in Spain. So we did pretty the same with this airline as well. In any cases, the current procedures from ICAO and X11 have been applied for airline operations, ATSU or rescue coordination centers. And for the COSPAS-SARSAT system, we applied the data distribution plan, which is the document reference 8001, and that you can find on the COSPAS-SARSAT website. So all these operations also strictly applied the procedures described in the new European ED277 and all the process described by Carmen just before. Okay, so what happened during this test case? So from France to Spain, so to illustrate what happened during this sequence, several events occurred from the activation to the deactivation of the distress tracking. So first, the Ultima-DT has been wake up as soon as the aircraft has been powered up, starting position acquisitions thanks to its internal GNSS receiver and ready to process any alerts. After the takeoff, so the trigger event for Air France operations and the French air traffic control was the scenario with the two normal tracking missing reports and no communication with the pilot. This is what you see at 153. So this action triggered the investigation phase as required in ICAO procedures till the declaration of the DETRESFA situation by the ATSU, which has notified to Air France operations and the Rescue Coordination Center this classification. And obviously, it was a Rescue Coordination Center in France here because the aircraft was in France, at least in the French airspace. So thanks to this classification of emergency, this action allowed the possibility for Air France operations to request a remote activation to Galileo with the service provider of such service today. So you can see that because every seconds matter now from this stage, even with manual actions for the test, the service is provided in few seconds from the request done by Air France operations to the first detection by the COSPAS-SARSAT system. So you can see here the request, the trigger of the Ultima distress tracking, and the sending and the detection of the location of the aircraft. So in only 20 seconds-ish in this test case, the aircraft has been detected, located, allowing the notification of the alert to the Rescue Coordination Center and the forward of the first position to Air France operations. So this is definitely a good success to see in less than 30 seconds you are detected and located. So the first position was available at Air France operations, and then the Ultima distress tracking obviously continued to transmit the position, refreshed positions. And then after a period of distress tracking in flight, safe conditions have been simulated and the return to a normal situation for deactivating in the same way the distress tracking. So this operation is possible only after a declassification of DETRESFA situation, and this is what has been explained. And as soon as it is declared, so Air France operations was able to request a deactivation. And again, in a few seconds, the ELT distress tracking, the Ultima-DT was able to start to transmit the cancellation sequence, which is in the specifications, and which takes roughly 2 minutes to be completed, allowing to record the end of the distress situation and to stop the operations really. Okay, so I give you back the floor, Carmen.
Thank you very much, Alain. Actually, just to conclude that the results of the flight tests were a success, and not only in terms of timing achieved, but also on the feedback that we received from Air France and also Iberia, that also participated in the test, and also the involved air traffic controllers and the rescue bodies. And we will listen from first-hand experience later on in the case of Enaire. So thank you very much, Alain, and I give back the floor to Christian.
Thank you, Carmen. And as you explained, yes, this is time, in fact, maybe for Anna to explain you and then present the floor, in fact, from Enaire.
Thank you, Christian. Good afternoon, everyone. My name is Ana Bodero. I'm part of the GNSS team of Enaire. Enaire is the Spanish main air navigation service provider. And I will explain very briefly our experience with this remote activation test that we did with the ELT-DT beacons. You can see here the test plan, as Alain explained before. It was a flight from Toulouse to the south of Madrid and back. Indeed, it was a very complete demonstration, as we had 2 operators, Air France and Iberia. And also we tested 2 different interfaces for the remote activation service. So from my point of view, it was really challenging and very complete. The experimental flight plan was previously agreed between Orolia and Enaire Operational Coordination Center. The real flight, we have to say that it was almost uneventful from an operational perspective. There were only several unplanned altitude increases that were authorized in real time by the controllers of Madrid to help solve some minor communication issues that we had with the SATCOM platform that we use for organizing the demonstration. We simulated activation and deactivations of the beacons from a room that we had next to the main air traffic control center here in Spain, located in Madrid. The simulation team was 2 GNSS engineers and 1 controller. Indeed, it was the chief of the supervisors of controllers. All communication flows were made by telephone, the important ones, the ones related with the distress situation, and following the provisions of Eurocae ED 277. At that moment, it was not published yet. We had a checklist agreed between all the stakeholders and a specific online interface that we used to communicate all the participants. And we think that this tool was indeed one of the key elements for the success of the demonstration. You can see here in the picture, an explanation of the communication flows during the Iberia test. The test, as we have explained before, was focused on the remote activation and deactivation of the ELT-DT and all the information flows. And it was not the intention to reproduce exactly all ATC actions in case of an aircraft is missing, in case of a distress situation. The Enaire ATS alert procedures, according to ICAO Annex 11, are tried and tested regularly, so there was no need for validating them at the same time as the remote activation of the beacon. So timing between the alert phase declarations was shorter than in a real case. What was the feedback of our controllers? Well, the remote activation, as we tested, we see that it doesn't modify or interfere with current ATC procedures at all. So good news in this point. The aircraft operator should always specify to ATC at its own initiative if the aircraft is equipped or not with this remote activation ELT. This is one of the recommendations of our controllers. We also see that it is not necessary to show in the ATC radar display the real-time ELT position once it is activated, or any alert, visual or sounds or wherever. It's not really necessary. However, the controllers would welcome the entry into service of some kind of online interface which can be accessed as needed, and where all the stakeholders, where the actors involved in a distress situation may communicate in real time and be aware of beacon position and status. So in this regard, the forthcoming ICAO ladder seems to fulfill these controller requirements. And also controllers would welcome that information is distributed among the controller community so as to raise awareness on this service. Also, to conclude, I would like to say that the controller's feedback was indeed really very positive with this service. And this demo created a lot of interest internally in Enaire. The added value is clear for the aviation community. And we, as air navigation service provider, we recommend to continue working in the implementation of this new service using Galileo for remote activation of the beacons. And that's all. Thank you, GSA and all the Helios partners for counting on us in this very interesting demonstration. Thank you.
Thank you, Anna. Thank you for your participation and recommendations, suggestions at the end also. In fact, thank you very much. Alain Bouhet will now share the Helios Consortium conclusions related to the test flights of the Ultima-DT system. Alain, it's yours.
Yeah, thank you, Christian. So yeah, I think as a conclusion, we can say that definitely ICAO and EASA requirements and this GADSS concept in general is very relevant and a huge progress to locate very quickly a crash scene of an aircraft. First, to save people. This is the major aim. And also to help Bureau of Investigations to perform the flight data recovery. So this is definitely a huge innovation, and it will change the commercial air transport definitely in the coming months. So we know that the COSPASAT ELT-DT as an EDT system has been also selected by all major airframers today. The Ultima-DT itself has been selected by Airbus on all programs and is in its integration process. And the Helios project has definitely changed the game and to find an aircraft, the people, and the flight data recorders. So this is definitely, again, a success. This flight test end-to-end validation, so confirms also the ELT-DT system maturity, at least in Europe. And this is also, I think, a very good demonstration of where we are to use this service. And this is also, you know, in the coming months that it will happen. So I think we have demonstrated the system is pretty ready, at least for this region. And even for the future service, so the possible use of the remote activation proposed by Galileo is also, you know, key for the air traffic control, the rescue coordination centers. It's for every stakeholders. This is also a really important step, which will be made probably in the coming years when it will be available for the service. And you know, Air France cannot join us today, but their representative told me that to repeat that they want to adapt the service and they would like to make it happen because they need it because of their history. So, so again, I think this is a very good success for this change in commercial aviation. And to conclude globally for the whole project, which is now over, I would like to thank all our partners, stakeholders, and contractors for their involvement and huge efforts in this almost 5 years project to make it a success. Yeah, so this is my conclusion and my last word. Thank you, Christian.
Thank you very much, Alain. I'd like to thank you, to thank also Carmen, Anna, Yoan, Alexandre for those very interesting and informative presentation. I'd like to say also just, you know, for Orolia, that has been a great experience, in fact, and a very good communication to the stakeholders, positive attitudes towards a new technology and new systems, even a bit in advance, in fact, of what is available today. So that was very interesting for us. So that brings us to the Q&A portion of our webinar. But before we get into the question, we have one quick poll so that we can make sure to follow up with anyone who wants to discuss the topics, any topics, in fact, we presented today in more detail. So you have just to answer here, to click here, in fact, if you want to be contacted, and we reach out to you via email. So we have a few, in fact, great questions to come from the audience during this presentation. So we'll present the question to all the panelists in general and ask one of you to respond. The first question, could you show how the Helios project will support the timeline for the implementation of the ADT, autonomous distress tracking system? Maybe Yoan to answer.
Yes, thank you, Christian. So I can answer from the COSPAS-SARSAT perspective because the Helios project has permitted to develop all the standards for the ELT-DT within COSPAS-SARSAT. So there has been a huge effort in the previous years to define the standard. In fact, there are two versions of it, first generation and second generation, but I don't know if I can go into much detail. And also something important is also all the certification procedure at COSPAS-SARSAT level to validate that an ELT-DT that would be sold on the market and installed on an aircraft has the correct characteristics and meets all the requirements that are specified by COSPAS-SARSAT. So definitively, the Helios project has played a major role in this definition of standard and type approval procedure. And also illustrated in this presentation, there have been different testing during the Helios project. Here we focused on the very last in-flight test, but previously there were additional tests with prototypes, and all these tests helped confirming that the level of performance expected was the right one, and we could meet this level of performance with the standard we were developing. So in this respect, we can say that the Helios project really helped to develop this ELT-DT standard to answer the ADT need. So maybe I will let Alain to complete on aspects that are maybe outside COSPAS-RSAT.
Yes, thank you, Yoan. Yeah, it's absolutely true. So, you know, well, the Helios members participated to many of the standardization activities. So mainly for COSPAS-RSAT, but also for aviation standards like EUROCAE, RTCA, but also ARINC, which develop you know, paper about the trigger in flight. So we participate to all of that. Now all the standards are published and stabilized, so this is really good news, and we can proceed on the certification now. So it's definitely good. We know that COSPAS-RSAT is also preparing the entry into service with specific actions, and we will continue obviously to support this type of actions. It's definitely good till the entry into service probably in 2022. Thank you.
Thank you. Thank you. Thank you very much. We have a second question. How the distress will be processed on the ground to address properly the specific case of distress? Maybe it could be Didier. Didier is with us. Do we have Didier Delcuvelry with us? Mute. Or Yoan. Maybe someone from CNES can answer this question.
Yes, I can answer. Let's say on the technical part and on the part related with the processing with the MeoLUT. One of the strengths of the MEOSAR system is that it will allow both receiving the encoded location in the beacon, which will provide the most accurate information to locate the aircraft. But additionally, as we've seen during the presentation, MeoLUTs are also able to compute independent locations, which means that in case of failure of the internal GNSS receiver, or even the GNSS receiver inside the aircraft avionics, we still be able to locate the aircraft. So of course, the location will not be as accurate as the one transmitted by the internal GNSS receiver, but still this information can be useful to locate the point of impact of the aircraft. So I think it's better than not receiving any information at all. And also, this independent location process is quite robust and cannot be spoofed, for example. So clearly, this is an important strength of the MEOSAR system. And then once this information arrives and is computed on the ground, then it can be distributed over all the COSPAS-RSAT network and associated entities that would need to receive this information.
Thank you, Yoan. Third question, how the GNSS core constellations contribute to the GADSS? Do all of them contribute in the same way? This is a question on the satellite and constellation side. Maybe Carmen?
Thank you, Christian. Yes, I will take this one. So actually, the core constellations contribute to GADSS in a different way. The first one and quite more obvious is the computation of the position in the ELT-DT. The ELT-DT normally has a GNSS receiver inside that may compute information from several constellations. Then also the different constellations contribute to MEOSAR by providing a payload that is able to transmit and relate the distress information that is provided by the ELT-DT. This is this is the case of Galileo, but also GPS and GLONASS. And in addition, what is unique and the unique functionality that Galileo is providing as of today is the so-called return link service. This is an additional channel that Galileo is providing that enables a possibility to introduce some additional information in the signal that is coming from the ground and from the satellite to the beacon. This is the functionality that we used in developing the concept for remote beacon activation, because by including additional information, it was possible to introduce the required information to request that the beacon to be activated when it is needed.
Thank you very much, Carmen. We have next question on the certification. Will EASA issue a certification review item for an airworthiness aspect of autonomous distress tracking component, ADT? Maybe Alexandre can answer this one, certification aspect of the aircraft.
Yes, no problem for this question. So that's actually a very good question. Thank you. As I said earlier, every time we bring a modification to an aircraft, we need to follow the guidelines given by the EASA. So on the specific case of an avionics system, which is the case for the ELT-DT, the applicable document is called CS-ACNS, so Alpha Charlie November Sierra, which is a document who gives all the guidelines that we need to follow to perform the certification of an avionics system on an aircraft. On that specific case of the ELT-DT that we're talking here, because it's a very innovative system, today it is not covered by the ACNS EASA document. Okay, so that happens sometimes when we have a new product, very innovative, coming into the market, and that the regulators are not ready yet for that product. So usually you will have to go with an alternative process that is called the certification review item, which is the word mentioned on the question. However, if you look at what the EASA has already done, and as I told a little bit earlier, they have already issued a draft proposal of an amendment to the CS-ACNS that will cover the ELT-DT. So most probably it's only a matter of time and probably a couple of months before the EASA will amend the original ACNS document to include the certification and all the worthiness aspect of that ADT ELT. Normally that was supposed to happen end of 2020 already. I guess the EASA had some trouble with it, probably because of all what happened. But to answer that question, I would say if you want to install that ELT ADT today, you will have to go with the certification review item. However, if you wait for a couple of months, which is probably what takes the project anyway, you will be able to use the normal STC process that is very smooth because the ACNS document will be updated at that time. So I hope it answers the question.
Thank you, Alexandre. Thank you very much. Interesting points, definitely. Last question on the possibilities to apply GADSS in military environments. It's a bit different. Alain, answer this one?
Yeah. Well, thank you for the question. I think So the distress tracking approach is definitely relevant for whatever aircraft. We know that ICAO documentation is already or includes already helicopters and general aviation as a provision for the coming years. And military aircraft, even if they are not in the civil aviation area. I would say that in peacetime environment, due to the nature of the transmission, it's just a question of ability to install the trigger in flight mechanism inside the avionic. But as soon as you have that, you can connect it to the Ultima-DT and allow transmission. So, so I don't see any technical stoppage to that. And in terms of use case, we know that sometimes military aircraft are also sensitive, and this is people to save. So it's really relevant. And for the other services like the remote activation, we know that today there is projects to extend over the civil aviation this type of service for maritime or land, for instance. So definitely it's a good point.
Interesting, definitely. Yes, we have people to save, definitely, maybe in delicate also situation, military operators could be. Yeah. Well, thank you. Well, that's all the time that we have, I think, today for questions. We close to reaching the end of the session. So you should receive our follow-up email shortly, including a link to view this webinar on demand, with a copy of the slides and contact information for our speakers. I'd like to thank you so much, our speakers and our audience, for your participation in this webinar. The Helios project has been a very good experience, and even more than that, you know, yeah, not experience, but in fact the I can't find any word now, you know, I want to improvise a little bit, and this is the way it is, but adventure, that's I want to say, but with real successes, and we continue to develop this technology. So we look forward to seeing you at the next webinar. Thank you very much, everyone. Bye-bye now.
Goodbye, everyone.
Bye.
Goodbye, everyone. Have a good end of day.
Goodbye. Thank you.
Bye. Thank you.
Bye. Thank you very much.
Thank you, Carmen. Thank you, everyone.